There we go. Cool. So obviously we've had a couple of weeks break. The online stuff has kept kind of tuning on. I will get to marking any assessments that need marking tomorrow. It's just been spending the past couple of days getting back into the swing of things. Cool. So tonight we're going to talk about volt drop. Who had a chance to read over the material regarding volt drop? Obviously there was some stuff in there, but we will go over it again. So we'll talk about volt drop, some key cable types and applications, and we'll talk about correct termination methods for different conductor materials. So first, a bit of revision. So where in AS/NZS 3008 1.2 do we find the base current ratings for cables? So thinking back to what we were learning about last time we met, where in 3008 1.2 do we find base current ratings? Yeah, it's all good. It's been a while. So we'd expected to find it in table 27 as 1. So in 3008 1.2, you'd find it in tables 10 to 13. So those are the tables in 3008 that give us our base current rating. And we must remember to do 1.2, 3008 1.2, because that's New Zealand. The 1.1 is Australian. Cool. So if a cable runs through an environment hotter than 40 degrees C, what do we need to do to its current rating? Yep, it's more than likely going to decrease. And what would we use to figure out how much we need to decrease it? Hard copy of 3008, most likely print it. You can download a copy from the EWRB standards portal, and then you can print it from there. You can take it to like warehouse stationery and get a printed and bound copy. That's probably the only way you get a hard copy, because the standards print cost is outrageous. Yep. So we'd go to table 27 or 27, so 1 or 2, and then we'd apply the temperature correction factor from that table. Cool. And what impact does grouping have on current carrying capacity when we bunch a bunch of cables together? Yeah. So chucking all those cables together will reduce current carrying capacity. Sorry. Screen. Yep. So basically, yeah, we decrease it because there is an increased risk of heat as well as possible magnetic effects because of the current flowing through each of the cables. Cool. So I've got a cable with a base capacity of 80 amps, and I apply a temperature derating factor of 0.87 and a grouping factor of 0.75. What's the new rating? So I've got a cable with a current carrying capacity of 80 amps, a derating factor of 0.87, and a grouping factor of 0.75. Yeah, so it's 52.2 amps. Cool. So what kind of factors affect a cable's current carrying capacity? Not so much length. Installation method, yeah, cross-sectional area or the size. Yeah, ambient tipping, heat, magnetism, conductor material. Yep. Has anyone got anything else? I've got a couple more. The ambient temperature, yep. Enclosed, yep. Installation method, yep. So another couple are your insulation type. So what kind of insulation does it use? So is it TPS, XPLE? Is it, even though you wouldn't use it now, VIR, Indian rubber? And what is the temperature rating of that cable? So those are things that affect the current carrying capacity. Cool. So last time we had a class, we focused on how much current a cable can safely carry. Today we'll look at what type of cables exist, where we use them, and how we terminate them correctly. But first we're going to have a look at volt drop. So even when a cable's ampacity, we're talking about its current carrying capacity, is also known as ampacity, is fine. We still have to make sure enough voltage reaches the load. Every meter of cable has resistance, and because current times resistance equals voltage lost. So today we'll look at two practical ways to look at that. So just give me a second. Cool. So volt drop calculations. So volt drop gets fairly important when you start getting into bigger cables or when you're getting into long runs. Cool. So we've got the simplified method. So this is not something, so it's good to learn this, but you will have to memorize this. Because I don't believe this is actually available. Cool. So relative quick method to find the volt drop of a cable in a circuit, or select a cable based on the maximum volt drop value. So some jobs you may be given a maximum volt drop value, and sometimes that is outside the normal 5% or 2.5%. So we have a base formula. AM per percentage VD is equal to I times L divided by the percentage VD or volt drop. Cool. So we all know I is the current flow in the circuit because that's what we've used when we've been looking at Ohm's law. Length is the length of the circuit. So how many meters of cable do we have to run out? Your percentage volt drop is the amount of volt drop allowed across the circuit. So expressed as a percentage. So for example, 230 times 5% equals 11.5 volts, and 400 volts times 5% equals 20 volts. So we're allowed a volt drop percentage of 11.5 volts or 20 volts if we're only allowed a 5% drop. So amp meter per percentage volt drop is the amount of current and circuit length that makes up each percent of the volt drop. I know that's a lot to take in. So here's an example. So a 0.5 mil cable has a value of 70 amp meters per percentage volt drop, single phase. This means that 70 amps flowing through 1 meter will cause 1% volt drop across that cable, or 2.3 volts. So 70 amps per meter. So 1 amp and 70 meters or 10 amps and 7 meters will cause 1% volt drop. This making sense or not really? Cool. Please sing out if anything's not quite clicking. I'd rather get it sorted now than it gets stuck later. Cool. So let's try and use this. Hey, Sean. Yeah, we're talking about volt drop. You've only missed a little bit. It'll be up online later as well. Cool. So the size of cable. So to size of cable, we need the load current, we need the length, and the allowed percentage of volt drop, e.g. 2.5% or 5%. So what size single phase cable would be necessary to carry 55 amps over a route length of 36 meters with a minimum voltage drop of 2.5%? Cool. So if our load current is 55 amps and 36 meters, allowed percentage volt drop 2.5, single phase circuit. So we always pick a cable whose table value is greater than that required. So amp meter per percentage volt drop required. So I times L divided by a percentage volt drop. 55 times 36 divided by 2.5 gives us 792. So the only one that's above that is 16 mil. So 16 mil is the next value up of that, 818. So this is the minimum size cable for this scenario. So what kind of scenario would we need to be able to work this out? I know that we have the volt calculation apps that we use, but what kind of scenario would we be looking at dealing with volt drop? Have you guys had to mains cable? Yeah. Anyone think of any scenario where you've had to do subboard to a garage or an outbuilding? Yep. Anyone think of any scenarios where they've had to do volt drop, or you think that the cable's been way oversized for what you would normally run for that type of circuit? Long run for a stove? Yep. Car park lighting, pumps, yeah. I've had to run 16 mil cable for car park lighting just because it was such a long run. If any of you guys work on street lights, the cable is running to film lighting, yep. Yeah, because the generators can't be so close to the film, so they would need to be quite a distance away. So you need to use the appropriate size cable from the generator. Yeah, the street lights, they run on quite massive cables underground. And then once they come up into the actual light pole, they're crimped and fitted off. And then there's only a 1.5 or 2.5 that actually runs up the pole to the street light. So yeah, when you're doing big, massive commercial jobs, or you've got to run a mains cable, all of a sudden, one example, there was a overhead mains cable in a property in Karori that was running across a a neighbor's yard. It turns out there was no easement. Does everyone know what I mean by easement? It's a bit of a legal term. Is anyone not sure what easement means? Okay, cool. So an easement is basically like breathing room. So an easement for a property basically means that it's a allowance for a service. So your property will have an easement for aerial trespass or aerial pass through of a mains cable, your sewer running into the property, your water, your internet. So there will be easements as part of the title or deed of your house. So there was no easement in the property title for that job to allow a new overhead cable or for a new cable to be run. So basically, the mains cable got damaged. It came down in a storm, and the neighbor wasn't very nice and basically said, "Nah, we want you to not run that across our property. You have no right to." So we then had to redirect it, which meant it was a 16 mil cable. It ended up having to be upsized to 25 because once we did the calculations of the length, we would have too much of a volt drop. So this is one example where you'd probably have to do the volt drop calculations. And yes, I know we do have apps that do it for us, but part of our electrician's exam, you may be asked to do these volt drop calculations. So which is why we need to know how to do it. Cool, but we need to remember that there are two different. Yes, we had to put in a new pole. Well, we got someone to put a new pole in, and we basically went, one way and then the other. Yeah, I think the job took us about 2 or 3 days from memories. Yeah, about 3 days. Obviously, the family was not. It would have been expensive. Someone else was. It was a state house, so state housing was footing the bill, and the family got moved out into temporary accommodation. So thankfully, no one was without power or any for too long. End of the day, I didn't get to see the bill. I kind of would have been interested to see. But yeah, one fun job I had when I was doing my apprenticeship. Yeah, 818, you can see in the table there. That's how we get to our 16 mil cable. Cool. So find the volt drop across the circuit. We need load current, root length. Cool. So what is the percentage volt drop for a three-phase circuit carrying 78 amps over 15 meters? Okay, it's supposed to be 150 meters. Wow, it really doesn't give you enough information. for 16 mil cable. So what is the what would our volt drop percentage be for 16 mil? Remember, we're using the three-phase. So three-phase number is a bit higher. Yeah, so we're looking at 7.12. So we take our 78 and times it by 150, and then we divide it by 1643, which is the 16 mil amp meter percent volt drop for 16 mil, which gives us 7.12. Okay, so what if we upsize it to 25 mil? Yeah, it's about 4.5% or 4.52%. There's the same calculations, but instead of using 1643, we use 2588. Now, what about 35 mil squared? Yeah, so 3.28 or 3.29%. You can round to 3.3. Yeah, that's how much percentage volt drop we would get at 78 amps over 150 meters for that size cable. Yeah, so we need to make sure we're using the three-phase circuit calculations or the values. So for 16 mil, yeah, 1643, we would get 7.12%. For 35 mil, we would get 3560, which would give us 3.29%, which is a lot better, especially if we don't want to. So for those of you guys who work in the supply, what's your allowable volt drop on the supply network? Yeah, about plus or minus 5%. So comes very important. Yeah, 5% on the power company side. Yeah. And then we have to make sure that we don't drop too low on our end. What could be the possible implications for having too much volt drop? What could be the consequences of having too much volt drop, not just on the network side, but once we get inside a installation. Yeah, undercurrent for power factor. Yeah. So we're not applying enough pressure to push the current through, and we can damage sensitive equipment or just general appliances. Cheap appliances won't run very well on lowered voltage. Some will. If you notice on a lot of the appliances, like heating appliances, it'll say 220 to 240 volt. So it allows for that voltage drop and spike. But yeah, not all appliances are created equal. Cool. So now finding the maximum length. So to find the maximum length, we take our amp meter per voltage drop, times it by our percentage volt drop, and then divide this by our current. So what is the maximum root length of a 16 mil single phase supply to a house designed to carry 63 amps with a volt drop of no less than 2.5? Yep. So we've got our load current of 63 amps, our amp meters per volt drop of 16 mil squared, our volt drop max of 2.4%, and it's a single phase circuit. So single phase, we know which column we're dealing with, the middle column. So our L max, so we have 818, which if we go down to 16 mil is our volt drop percentage, multiplied by our volt drop max of 2.5, and then we divide that by our 63 amps. Which gives us 32.46 meters, or 32.5 if you want to round up. But more than likely in this, you'll want to round down to 32.4. So that's how long our mains can be without getting that 2.5 volt drop. And this is the detailed method. So this calculates volt drop using the cable's volt drop value, VC, and MVA meters. So this is ASNZS 3008 1.2, along with the load current and root length. So base formula, volt drop equals VC times I times L divided by 1,000. So the current I, length L, VC is a constant. That's the amount of volt drop measured across 1 meter of specified cable when 1 amp is flowing, measured in millivolts. And then volt drop, total volt drop across the circuit when all factors are taken into consideration. It's measured in volts, which is why we divide by 1,000, because the VC is in millivolts. So we have our conductor size down the side, our maximum, and with a 0.8 power factor. So 1.5 has a B75 cable will drop 28.6 millivolts per meter of cable per amp of current flowing at max power factor and 3-phase. So these are 3-phase values. To convert to single phase, we multiply it by 1.155. When you get to the exam, you will, so 3008 1.2, you're not allowed to take into the exam. Whereas table 442 is in 3000. So it will pay to take this down. I'll give you guys a bit of time to take notes. It will be in the video, but it is good to know this method. The formulas should be in the section. I'm just trying to look up now. While you guys are taking that down, and then we'll take a 5-minute break, and I'll be right back. Cool. Yeah, the simplified version is in table C7. So you will go over this a lot when you get to regs, depending on who's doing regs. Hopefully it's Dave, who you guys all met when you did block course. Hopefully, some of you. Yeah. So Dave is currently teaching regs online. It's basically if you find the answer. So you'll be given a scenario like we were talking about before, and you'll have to tell them whether what size cable to use or what the volt drop is or the maximum length. And usually they won't be that close that you'll be able to get them confused. So cool. Don't have to worry about the complicated version. But yeah, simplified version is the easy way to go. Cool. So yeah, we talked about 1.5 V75 cable, 28.6 millivolts per meter. And just like so, to convert the single phase, convert to single phase, we multiply by 1.155. Cool. So a circuit that is 40 meters long has a load of 25 amps attached to it. The cable used to supply it is a 6 mil copper V75 cable, and the load is purely resistive. So I, 25 amps, length 40 meters. So 6 mil, 75. So the temperature is 75. So when we talk about cable, V75, V90, V60, it's the conductor temperature rating. Cool. So 6.49 millivolts per amp meter. So volt drop, VC times I times L divided by 1,000 gives us 6.49, which is our VC, times 25 times 40 divided by 1,000. Cool. So 6.49 V single phase or 7.5 volts three phase. So if you notice, we're looking at the max. Why are we looking at the max under the 75? Not to overload it? Yeah, there is another reason, and it's in the question. Yeah, resistive load. So the power factor has not changed. Because it is a purely resistive load, we can leave it at its max. Cool. So now let's talk about cable types and terminations. So some of our standard ones you'll come across: TPS, or our thermoplastic sheathed; elastomer sheathed or rubber; XPLE or XLPE; neutral screen; and high temp. So some key features. So TPS is usually flat or circular. It has a PVC insulation, and sheath. Typical applications: your domestic lighting and power circuits, as well as your commercial power circuits, and probably a little bit of industrial too. So elastomer sheath rubber, flexible, impact, abrasion resistant. So where might we use this? Outdoor areas, yep. Extension lead, yep. Industrial, warm rooms. So, outdoor extension leads, portable tools, and industrial equipment. So that's where we would use our elastomer sheathed rubber. And yeah, warm rooms or areas where there's high temperature. So XPLE is cross-linked polyethylene insulation with high temp rating. So this is what we'd be using for our high temp areas. It's usually used for mains, sub-mains, and large feeders. So this is where we're not using neutral screen. So if you've done any commercial or domestic work and you've had a red and a black core and it looks like TPS, it's not TPS, it's more than likely XLPE. And then our neutral screen, so it has a screen around the around neutral for fault protection. So that way, if you pierce the cable, more than likely you're going to hit the neutral first, then the phase, causing a dead short. So it's used for certain main suppliers and metering. What is hard drawn? Can anyone give me an example? Tell me what hard drawn is when I'm talking about this kind of cable? Yeah. It's the stuff we use for aerial mains. It is a lot tougher and a lot more rigid, so it can support its own weight. It also really hurts if someone hits you around the leg with it. Not talking from personal experience or anything. Yeah, I made some mistakes, okay, and it was back in the day before HR. Yeah, yeah, just don't hit anyone with it. It's not nice. Yeah, it really hurts when you hit around the ankle with a piece of hard drawn.
For the people that don't listen,
Like I was talking about, Dave.
come on. Volt drop. Are you on volt drop?
We mostly talked about the simplified method.
Yeah. So just so you guys know, the volt drop standard is AS&Z 30081.
Yeah.
And that has most of it in there. Other than that, it's in section C of AS&Z 3000.
Yeah, they found the table in section C.
Sweet.
Yeah, so the simplified method is what they'll have access to when they actually do their exam. 3000 you're allowed to take into your regs exam.
So is this the theory and regs?
Yeah.
In theory and regs, you won't just use the simplified version. You'll use. Actually, I've never seen the simplified version in an exam. In your exam, you'd use the standard long term with using all the tables, table 11 and all that too.
Do you get given 3008?
No, you get a snippet out of it. So in your exam, there'll be a little table that you open up and that will give you the additional parts to get the information from it. So if I remember correctly, on C4 is a simplified volt drop, and just above it is your volt drop formula. So that will be there, and then you'll get a snippet of 3008, and then you'll get access to table 42, 11, 13, 27.1, and 27.2.
Yeah. And when you guys go to do your capstone online, they will give you the information. They can't not give you the information when you do your capstone at the end of the year, by end of your year, which will be next July, June, July. So anything you need to answer the question will be given to you. They can't not give you the information. They may give you too much information, but they will give you information.
I'll get Stu to give you some paper handouts or email through some handouts that you would use more. The paper handouts will be online because it's your capstone is online, not in a paper form.
Yeah, so you'll be given, when you get the question, you will have some tables given to you or snippets of tables, and it's up to you to figure out which snippet you need to use. And as far as handouts, they've just got a Google Drive that they can access, they can upload to.
Yep. So I'll give Stu the standards and everything else, and he can upload them for you.
Yeah, and anyway, hopefully, well, most of you guys should be coming here for your next block course early next year. So we'll hopefully see you then. Yeah. Yeah. High temp cable. So special insulation, usually silicon or fiberglass. I've never got to play with it. Have you?
I turn cable all the time, baby.
Yeah. Cool. So it's used for ovens, furnaces, and industrial heating zones. So not something that your general house sparky will get to play with. What else do we need to talk about? PDF. Love how they give us lesson plans. Cool. So when you're installing any cable, there's certain rules and guidelines you need to follow to ensure safety, reliability, and compliance. Things like minimum bend radius, mechanical protection, and support spacing. But why would minimum bend radius be important? What happens if we bend the cable too sharply? Yep. Don't do that.
That's not cool. That creates fires.
Yep. So your high resistance is going to cause hot spots. The amount of times I've gone into opened up commercial boards in apartment buildings, and I've seen a cable 16 mil that's been kinked almost to a 180-degree bend, and not a nice sweeping bend, nice kink bend. The joke that me and the boss always made was the apprentice liked to get kinky with it. Don't be that. Don't be that one. At least not on the job site, please. Cool. So anyone seen TPS run without protection where it really should have some?
Like in your garage.
Yeah. Or it's been painted green. That was cool. Oh yeah. Our those of you who are on the outdoors with paint. Oh yeah, that's might protect it from UV, but it's definitely not good enough mechanical protection. Cool. So good termination can be the difference between a paint's extra insulation. I think you need to add at least 2 or 3 layers of paint for it to be.
Just remember, paint means that heat can't disperse out of the cable. So the cable's protection is rated for up to 75 degrees Celsius. With paint, you're making sure the cable's not going to get any heat out of it.
Landlord special, yeah. Cool. So good termination can be the difference between a reliable circuit and a fire waiting to start. Cool. So copper versus aluminium. So copper is the most common type of cable you're going to come across for final sub-circuits. Here in New Zealand, we use copper for our sub-circuits. It's generally, as far as I know, sub-circuits run in aluminium is only allowed, mostly done over in the UK, US and Canada. It's light, aluminium is lighter and cheaper for large mains cables, but more prone to oxidization and creep, and needs to be a bigger size because it does not conduct as well as copper. So if you look at the table of current carrying capacity, copper versus aluminium in 3000, you'll notice that the copper cable is a lot smaller most of the time for that rated current. And has anyone had to join copper and aluminium together before? Anything else? Okay, those of you who did, how did you do it? Learning curve, how'd you do it? Transition crimp or shear bolts? Yeah. Special kind of link. Shear bolts. Yeah, cool. So it's really terminated directly into stranded terminals. It's usually got tailed onto copper. So it's called a bimetallic lug, and it usually has a dielectric grease inside of it to stop any corrosion and stop any creep between the two metals. Normally you're going from like 125 mil aluminium down to about 25 or 16 copper. So there's usually, it's pretty obvious which side goes on which, and it's full of anti-oxidizing compound, which is essential for aluminium terminations. So if you look inside of your aluminium lugs, you'll see a nice big glob of glue. Lube, more like lube, not glue. And you really need to kind of work it around onto the aluminium to make sure it gets across all of it. Because if you don't kind of wiggle it around, you'll end up with some spots that don't have any oxidizing compound on it. And that's where you'll get that high resistance joint from the oxidization. So what's some common termination devices that you guys have used in your everyday? Bootlace or ferrules? Yep. Hex crimp, so lugs. Strip connectors or screw connectors? Yep. Crimps. What's the Wagos? Yep, the new ones that are becoming more common. Compression fittings. So crimp strip connectors. Yep. Cool. So when we terminate our mains, earth or main neutral, or our, I guess you would technically have main, even your main phase, you don't have to do that. So what is the requirement for connecting your main earth and neutral? MEN link, well, we need to have one in the installation. Double nut. 2 nuts on bar, yep. So the general rule is double nut or double screw. So if it's going into a tunnel type with screws, you need 2 screws onto that. If it's going onto a post, it needs to have double nut. And at least all the inspectors I've worked with will get really annoyed if you put 2 lugs on one post. So make sure you've got enough posts for the amount of lugs you need to put on. Cool. So 3000 requires joints and terminations to be both mechanically and electrically sound. So we need to insulate it to the same degree as the cable and protect it from damage and moisture. How many of you guys don't put heat shrink over the lug? Yeah, collect all those old Imperial nuts and keep them in a jar, definitely. Whenever I take a switchboard apart, I keep those, always. So how many of you guys don't put heat shrink over your lugs once you've crimped them? Looks like everyone, good. Cool. So that's what we're going to call it for the teaching section for tonight. Obviously, you guys have had 2 weeks break, so if you guys have got any questions, feel free to offer them up. Odds are someone else is scratching their head about the same thing too. And now you've got 2 tutors to answer questions now. Just waiting for Dave to run away.